Hello friends. Today we are repairing a thermostat for heating. The problem is that it burned out and does not work as the client told me. You see the name. Now I'll take it apart and see what the problem is. Yes, friends. As you can see here, it's clear that something has burned out. I now see at least 2 burnt elements. On the reverse side, everything seems to be intact and there are no burnt elements. You will need to clean off the carbon deposits, but this is not a problem. The problem is that the burnt elements are now impossible to discern what melted there. Most likely I will need to find the same module, only a working one, in order to understand what was installed there. I found the same thermostat as mine, only it works. Now we will figure out what burned out on the board. Well, the first thing that catches your eye is that the thermal fuse has burned out. It was simply torn apart. An element called TF1. Let's see what it looks like when whole. The fuse is designed for 115 degrees. This is the first burnt element and the next one is L2, an inductor in SMD format only. In appearance, this element looks like an SMD resistor or a SMD capacitor, but in fact it is an inductor. I don't see any more burnt elements visually yet. There is another inductor here. It is black on the side. Perhaps it has burned out, or perhaps this is carbon deposits from another burnt out radio element. The coil is called L1. I wrote out the names of the elements and their denominations on a piece of paper. TF1 is a fuse. L2 is an inductor. L1 is also an inductor similar to a barrel with ratings of 10 mH or 10,000 microhenries. R18 is a resistor marked 122 on it. It is equal to 1.2 kOhm. It is SMD and is located between the capacitor and the inductor. In general, the suspicion is that 2 inductors and a thermal fuse are still faulty. I don't have such a thermal fuse, so I'll make a jumper. I'm also unlikely to find the same inductor, so I'll probably install the jumper in the same way as with the thermal fuse. And friends, I completely removed all the elements here and it was not in vain that I did it. Because I saw that under the capacitor the track was broken, which goes from the capacitor to the burnt inductor in the form of an SMD. We will now take a closer look at this under a microscope. I haven't seen any more damage yet. I'll take a closer look under a microscope. I cleaned everything here of black carbon deposits. I also discovered that one leg of one capacitor had almost fallen off. The capacitors will also need to be checked, but for now let's check the inductor, which is suspicious. We put the multimeter in dialing mode, then we try to dial. We should not have much resistance. In dial mode, the multimeter shows 94.2. Let's now check on a worker. It shows 94.4, which means it is working. It turns out that only a small inductance burned out. Let's take a look at it under a microscope. And we'll also need to check these 2 capacitors. Let's look at the SMD inductor after damage. And friends, we look closer. As you can see, part of the side of the inductor has melted. This coil is definitely a replacement. But maybe I won't find one and will just make a jumper. Let's also take a look at the board. Here we have a diode bridge, then the track goes to the capacitor, and then, as you can see, there is a break from the capacitor to the inductor. And also on the other side, the edge of the path is damaged. You can, of course, get confused and look for a coil with approximately the same characteristics. But this element has virtually no effect on the operation of this device. Here are some more friends. A more accurate way to check an inductor is with a transistor tester. We connected it and now we check. As you can see, it shows 8.4 millihenries, but in fact it should be 10 millihenries. In any case, there is an error both in the element itself and in the measuring instrument, so the coil is 100% working. Now let's move on to capacitors. Our capacitors are 400 volts and 2.2 microfarads. Let's see what the transistor tester shows us. So it's interesting that I didn't define the element at all. Maybe it's not working properly. This shows 2000 nanofarads, ESR-21. So let's look at the second capacitor. Shows approximately the same characteristics, approximately 2000 nanofarads. As far as I remember, there are 1000 nanofarads in 1 microfarad. It turns out that it is close to the required characteristics, but the ESR is suspiciously high. Let me check my spare capacitors and see what the ESR is. Shows 1.1 ESR. In terms of capacitance, the capacitors are almost normal, but in terms of ECP, the characteristics are too high compared to other capacitors. I also suggest checking the capacitor from the working thermostat and comparing the characteristics.
The capacitor shows almost 2.2 millifarads and ESR 8.2, which is much lower than with those two capacitors. Therefore, you should still change them. And so friends, I bought two capacitors. The price is 10 cents. But getting to the store is of course problematic because it is quite far away. The new capacitor is the same at 400 volts and 2.2 microfarads. Let's check it with a transistor tester. ESR shows 6.5. It turns out that approximately ESR up to 10 is the norm. Then it is better to change the capacitor.
Now we install new capacitors. I made the jumper as follows. Behind the board I connected the legs of the capacitors. I tried to start the device and unfortunately it did not start. I checked whether the display was working at all. Otherwise it might be damaged. Then I connected the display to the working board and it worked for us, which means that the problem is in the main board and not in the display. This means there is still some element that is not working. I unsoldered the resistor marked R20. It is located in this place to which I am pointing. The marking on the resistor is 5-band. And on the reverse side I found a defect on it. Perhaps it is faulty. I also unsoldered it from a working device and we will now compare them. The working resistor shows 10 ohms. The marking of the strips also shows that it is 10 ohms. Let's connect a resistor with a defect. As you can see, it is not detected and there is also a defect on the body. This means that it is faulty. It turns out that we need to replace this resistor. The resistor is large enough at 10 ohms. Now I will look for such resistors. And so guys, I replaced this resistor with a 10 ohm one, only it has less power and it itself is smaller. I hope it will be enough to test this device. In the future I will replace it with a larger size. So I tried to turn on the thermostat again and it didn't turn on again. I discovered another problem. When measuring at the input we have 220 volts and for some reason the voltage does not come to the diode bridge. It turns out we have a break somewhere. Let's look where. I completely disassembled and desoldered all the parts to see what was under the relay itself. Phase and zero are connected to these two contacts, and phase does not come from some side. The path that goes under the black relay just doesn't come and didn't ring. Let's figure out why. We have a track here that passes through the board and it should be dialed. On the reverse side it is here. It looks like there was a loss of contact at this point, and therefore the phase did not reach the diode bridge. That is, this place needs to be properly soldered or a jumper made. You can make a jumper out of wire and then the contact will certainly not be lost, although it may prevent the relay from fitting tightly into place. Yes, I think so. It will still rest on the relay. Since I was unsoldering the relay here and most likely I have already soldered all the bad contacts. Let's try to call her. Yes, now the track is ringing. It turns out that the contact has disappeared either in this place or on the small board on which the relay is installed. Since there are through holes on it, there is also contact here, but I desoldered it and, accordingly, most likely I restored the contact without knowing it. Now we put everything back together and now the tracks should be connected to the diode bridge. There is also a track from which the insulation has fallen off, apparently from heating. But it is not damaged and rings. Perhaps I'll tin it to strengthen it. Our square capacitor is 198 nanofarads. The marking says 200, the capacitor is working. Therefore, we install it in place. Let's try to start it again. In theory it should work now. And so we try. My traffic jams were knocked out and my lights went out. The resistor simply broke. Perhaps it exploded because I put it in a smaller size. Let me install it from the working board and run it again. Well, let's try. Friends, take two. Moving on. It means there is still a faulty element in the circuit. I removed the diode bridge and checked it. Our diode bridge is short-circuited. How to check it? Using a laboratory power supply. We supply voltage to the diode bridge. There should be no current consumption, and the output should have the same voltage as the input. I'm just showing you a working diode bridge. If you connect a burnt one in the same way, it starts to heat up and shows high currents, which indicates that the diode bridge is faulty. We have a diode bridge called MB6S. Now my task is to find the same or better characteristics. I looked at the characteristics of the diode bridge that burned out, and the following is indicated there. It is designed for a maximum current of 0.5 amperes, after which it burns out. I will now install an MB10SL diode bridge instead. It has a throughput current of 0.8 amperes. It turns out better than the one that was standing, so we will install it now. Let's try to start this device again by installing a small resistor again, because there is no larger one and I have already ruined the working one. And so friends, let's try to launch it again. Take 3. This time the plug was not knocked out, but something began to smoke and stink. This means there is still a faulty element. This time I also changed the PWM controller and again the input resistor. Let's try to launch it again. Yes, friends, and this time everything worked for us. Friends, I finally defeated this device. It turns out that a whole bunch of radio components on this board burned out. As you can see, the buttons work and now the thermostat is working normally. Let's summarize what elements burned out on this board. Let's see what components burned out on this board. The first is a thermal fuse. I made a jumper instead. You can buy it and install it. I showed it earlier. The second is a PWM controller. Third, this resistor called R18 with a rating of 1.2 kilo ohms burned out. Fourth, I changed 2 electrolytic capacitors. Fifth, the diode bridge burned out. Sixth, the input resistor burned out 3 times when I tried to start the device. Seventh, the contact from the input to the diode bridge was lost. And 8th, the track from the capacitor to the inductor burned out. 8th, the small inductor burned out. So friends, how can you check the LNK500 PWM controller? It has 3 outputs, C, S, and D. The legs of S, they all call each other. If you put the multimeter in the dialing function, then all the S legs should ring with each other. S and C should not call each other. S and D should not call each other either. S and D should not be called either. In my case, S and C were called, which means there is a hole between these legs. Therefore, my PWM controller was not working. I have now shown you in detail on the diagram how to test such a PWM controller. The counting of the legs comes from the key, which is shown by a circle in the corner of the PWM controller. I bought resistors a little more than what they cost because I forgot to take a sample with me. You can install larger resistors, but I don't recommend smaller ones because they may not withstand the heat and will burn out. I will also melt solder on the reverse side to strengthen the tracks. Next we will assemble this thermostat. As you can see, the thermostat is now working. Congratulations! The device is now back in action. Next we put on the top cover, and that's it. Well friends, I hope the video was useful. Don't forget to thumbs up and see you soon. Good luck with your repairs.